Hi, Eric. How are you?
I am fine, Susan.
I have a question for you today, if you don't mind.
Not at all.
Um, I know that Eddington devised a way to prove that Einstein's theory of relativity was correct. Can you talk a little about that?
I would be very happy to, because that is one of the seminal experiments or measurements ever carried out in cosmology. It is quite easy, as we have done in the book, to show that the Newtonian version of gravity, while it gives the right answers in many cases, is rationally totally untenable. However, since it does give rational, correct answers, as does Einstein's theory, we have to compare the two and determine which one is correct and which one is a uh, observable manifestation of some other underlying mechanism, which the Newtonian theory in fact is. But we need to prove that. Now, Newton basically says that space is the same all over once you get outside of the Earth. It just doesn't change. But if an object approaches the Earth and exerts a force on that object, which accelerates it at a faster and faster rate down to Earth until it impacts the Earth. And when we observe it, that is sort of what that is like. Einstein said, no, that isn't what's happening at all. There are no forces acting on that object. What is happening is that the space around the Earth is being compressed more and more as it gets closer to the Earth. And the reason that an object coming in appears to be accelerating is because it's traveling through an ever smaller space. And it turns out that the space gradient and the acceleration gradient that Newton used are mathematically exactly the same, so they will give the same answer. But only one of the two models is correct. There is a duality here between gravity as we teach it in schools and gravity the way Einstein sees it. The gravity we teach in schools, it's very easy to teach. All of these forces are all rational. We can all sort of imagine them. What Einstein says, we cannot imagine. It's something that is happening on such a small scale that it is an unobservable phenomenon. And what we are seeing in Newton is the observable manifestation of the contraction of space. But you've got to prove it. You've got to say, run some sort of observation or experiment to say, okay, Newton, space the same all over, but forces acting. Einstein, space is compressed and there are no forces acting. Well, what can we test? We can test the latter observance. We can test the idea, is space around an object like the sun, for example, compressing or isn't it? Now, if it's compressing and is compressing at the rate that Einstein said, the light coming around the sun would bend and we would see a distant star, not where it really is, but on projecting back on the bent line. But the problem is, if the ray goes past the sun, the light of the sun will make the experiment impossible unless there is a solar eclipse, which means that the sun is in the way, but is being obscured of the moon cutting out the light of the sun. So the sun is there, and if Einstein is correct, the light will still be bending, okay? And the position of the star will appear to have changed. So is it going to happen or isn't it going to happen? Well, he had to take his equipment, go to a place in a distant part of the world, set up his telescope, which we call Eddington's eye, for reasons that we will discuss later on in the book, and measure it, measure where that star is, and then measure where that star is after the solar eclipse. If it has moved the distance predicted by Einstein, Einstein is completely correct, indisputably. If it didn't, Einstein is wrong and Newton is correct. So there you have it.
Wow. That was
Is Newton's form of gravity an observable manifestation of what is actually going on, the totally unobservable contraction of space, or isn't it? And if it is, then all of these forces that you learn about as a school child don't exist. It is
Although
the contraction of space that exists. Now,
right.
I'm not suggesting that we change the curriculum in schools and say, okay, but it might not be a bad idea if we don't teach Newtonian conception of gravity as though it's real. It isn't. And maybe it's high time that our educational system learned to make a distinction between what seems to be the case and is a very nice model to make the calculations easy, and what is actually going on. It might put a new perspective into children's minds, but I don't think it's going to happen.
That's great. And on another day, you're going to tell me something about how maybe it doesn't exist the way we think it does, but something does happen when I let go of the pen. It reliably drops. We'll save that. Okay, we'll save that for another day.
On another day, Susan.
Okay, thanks, Eric, so much.
You're very welcome.